So the last thing I just explained is that in Python, you can actually, the user can choose which command line argument, which arguments he wants to pass to a function, and in which order he wants to pass it, making it more user-friendly compared to regular programming. But there's more technical differences between scripting languages and regular programming languages. And there's different ways on how you can classify them. One is how these languages are typed. And essentially, there are two different ways on how you can type variables in a programming language. It can either be dynamically or statically. Python is dynamically typed. And what that means is that if you create a variable in Python, let's say c equals 1, making c an integer. Right? So if you ask Python which type has c here, it will tell you it's an integer. But in the next line, you can use the statement c equals bracket 1, 2, 3, making c suddenly a list. Right? And so the variable type can dynamically change in the program. That's what it's called. That's why it's called dynamically typed programming language. And Python is one example. The contrast of that is if you have a static programming language, like C. So in C, before you start using a variable, you have to declare which type that variable is and will be through its entire lifetime. So you say, OK, I have a variable C. It's a double. It's of a double, which is a floating point value. And then you can assign a value to it. For instance, c equals 5.2. So that's going to be a valid statement because 5.2 is indeed a floating point value. However, if you try to add the statement c equals, and then you add a string on the right-hand side, it will fail because you specified that c is going to double and it may never change. Right? So that's a statically typed language. You define once what the type is and it may never change. Another classification is weak versus strong typing. Right? So before we had dynamic and static. Now we're talking about weak and strong typing. So an example for weak typing is Perl. So in Perl, what you can do is so Perl is this bit strange syntax where you use the dollar in order to indicate variables. So $b equals, and then you use a string on the right-hand side, 1.2, right? And then on the next line, we say $c equals 5 times $b, right? And so now Perl tries to be clever, and it says, OK, you have a number multiplied by something that is a string, but actually the string looks like a number. So I'm just going to assume that you mean 5 times 1.2, and it will give you, well, whatever that is, 6. Yeah? So that's weak typing. So the type may change depending on what the programming language thinks what you want to do. Right? Yeah. Which I don't think is such a clever idea, but Perl does it this way. So Python is strongly typed, meaning that an object or a variable has a type, and it will always operate on that type. It won't just change magically. So here's an example. What you can do is in Python, you can do b equals 1.2. And then you can actually write c equals 5 times b. But the result is not going to be 6. It's going to be something else. And we can try this out. The result looks like this. Right? And the reason for that is because in Python, the star operator is operating on a string. And what the multiplication with the string does is that it multiplies the string. It just concatenates that string 5 times. Okay? So this is a multiplication of a number with a string, which gives you a longer string. So now, let's say we wanted to try out something else. Let's say we try to compute the exponential of a string. Right? And so if you do that, you get a type error. You get an error saying, you've passed in the incorrect type. You need to type in a float, but you provided a string. So in Python, the Perl would just change the type dynamically. It would just say, oh, well, probably you want to just try to convert that string into a number. So if you want to make this last example work, what you need to do is you need to explicitly convert the variable b into a floating point value. Right? So this function float, it takes in a string and it converts it, the type, into a float. So then the result here is going to be a floating point value, and that you can pass into math.exp, and then things work again. Okay? So that's how you can differentiate weak versus strong typing. Then there's other types of how you can classify languages. For instance, languages that are interpreted versus compiled languages. So essentially all scripting languages are, well, from a user's perspective, interpreted, so there's no compilation or linking step. Then there's high-level versus languages. High-level meaning that a lot of the technical details are hidden from the user, and you don't actually have control over these details, while low-level languages give you a lot of control of the technical details. So if you like memory management and then doing these kind of low-level operations, then you should choose C. And there's scripting versus system languages and different ways on how you can classify different languages. So here's an example here's a problem setup for something that is actually not possible to do in C, but only possible to do in a scripting language like Python. So let's say, so the problem that we're facing with is that you have a configuration file, and it's essentially a file that contains assignments, saying a equals 1.2 and n of iterations equals 100. So it's a file that kind of, in this case, it describes the setup of my simulation. And it's a text file, and I want to kind of change that configuration file, and my simulation should then use it. And so what I want to do is I want to read in this file and essentially execute each line in Python. Right? At the end, after my program is run, I want to have a variable called a. I want to have a variable called number of iterations, solution strategy C1, C2, and A, with these values here. Right? So essentially, the task is now to read a file and execute the commands that are stated in that file. So how do we do that? So in Python, the solution is shown here on the top. What we do is we open our input file. This just means read only. And then we get a file handle. Right? And then we start, we have a for loop where we essentially loop through each line in that file. Then what we do is we split the left and right-hand side of that equal sign. So I want to get the variable name and the value. Right? The variable name is on the left, and the value is on the right of that line. So I split by the equal sign and get the left-hand side and the right-hand side. Then the next line is called strip, which in Python means remove all new lines and white spaces and so on. So we essentially only get the on the left and right-hand side of that string. So we only get the actual important characters of that variable. And then what we do is, so if you look back, some of these configuration names here had white spaces, and that's not a valid variable name in Python. So what I'm going to do is I'm just going to replace that white space here with a underscore. Right? That's what's going on here. So I say variable equals variable.replace white space with underscore. And then here's the magic line. So here I execute a string, and the string has to be a valid command in Python. And so what am I executing? I'm executing the variable name equals the value that I've read in from that line. And after I've executed that, the variable will be a valid variable in Python. Okay? So essentially, if I run this, and here in the last, I just tested, I print the value of A. So let's test it, and indeed it works. I get the value 4. And if you look at the previous slide, that's exactly my value that I've chosen here. Okay? So this can actually not be done in compiled languages like Fortran, C, and C++. Any idea why? No one? Well, in compiled languages, you have a compiler, right? So the program that your source code needs to be available before you run the program. Right? So you first write the program, then you compile, and then you execute it. While here, we're adding dynamically new commands to our program. Right? So here, we would have to, the only way how this could be done is to first add the configuration file to our source code and then compile. Right? But that would defeat the purpose of our problem setup. Right? We want to be able to change the configuration file without having to recompile our program. Okay, these are some advantages of scripting languages, but they also have disadvantages. And the disadvantage that you will probably hear the most is that scripts can be very slow. And the reason is because, the prime reason for that slowness is because they're not compiled, right? And so the compilation step allows for a lot of optimization that can be done if you interpreted your language. But that's actually, when I say they're interpreted, that's actually not entirely true, because there's a kind of a bytecode compilation step automatically happening when you run a Python script, right? But as a user, you don't actually see that. But what really is happening is there's this bytecode compilation step, and then this bytecode is interpreted in Python. So when you run a Python program and you check the directory afterwards, you will see that there's a new file appeared, and it's the file name of your script, .pyc, right? And that's the byte compiled version of your script. And it's actually that one that is later on interpreted. Now, even this byte compiled version is not going to be as fast as, for instance, the C version. So for text processing, you typically obtain, if you do some performance tests and you do that on tasks that involve a lot of text processing, there you actually get to a fairly similar speed up than compared to a C program. However, if you do some loops over large data structures, let's say maybe reading in an entire movie file and you're looping over each line in that file and do some operations on it, right? It would probably look like this. Right? That's going to be really, really slow in Python. And the reason is because compiled languages can optimize these loops and hence lead to much, much faster assembly code. So in practice, you can, if you compare such a loop here in Python and C, you probably get a slowdown in Python of 100 to 1,000. Now the good, okay, so I mean that's a bit sad, but the good message is that what we can do is, or what one often does is, one writes the Python script, one identifies the slow loops, and then one converts these loops into C. And one just replaces the slow parts of your program in C and uses the C version from your Python program. Right? That's how you get around from the flexibility and the productivity of Python with the speed of C and C++. And that's going to be one important part of this course. Oops. So here's some performance tests that I've run for one of the loop essentially that I've shown you before. So I've read in 100,000 lines from a data file that essentially contains X and Y data that I wanted to process. And what I wanted to do with them is I wanted to write a new file that contains X and a function f applied to the Y value. Okay? Okay, so and then I've implemented that function in various different programming languages and timed it so you can see how long it takes. So in pure Python, 100,000 lines takes 4 seconds. If you do the same thing in Perl, it takes 3 seconds. Tcl takes 11 seconds. Okay, but now it becomes interesting. So if you do pure C, you can get immediately down to 1 second. So it's already 4 times faster than Python. If you do pure C++, you actually need 3.6 seconds. So C++ and Python are almost competitive. If you use buffered streams, you can speed up that C++ version a little bit, and you get down to 2.5 seconds. But now, if you use the numerical Python module, so you use some modules that are actually designed for reading in large data and processing numerical data, you can go down from the 4 seconds to 2.2 seconds, and we are competing, and we're actually exceeding the performance of the C++ version. But we're still away from the C solution. Okay? So 100,000 data points isn't very much, right? If you want, it would probably be more interesting if you actually read in 1 million or 10 million data points. But this still tells kind of the main story. And if you wanted to read in more data points, it's also not a good idea to process this in text. So I had this in text format. Right? In practice, what you would do is you would have this data stored in binary format, which would give you a lot better, much better performance for all of these solutions. So to summarize, when is scripting convenient? So one of the setups is if your problem on hand consists of connecting different pieces together. Right? So maybe you have, maybe you want to do some, call some other applications, do some text processing, and then call another application, and then use that output of the application for another application, right? So essentially, you want to connect multiple pieces to one big system that solves your task. Another case where it's really useful is if you don't know exactly yet what you want to do. So maybe you want, especially the design of the application, maybe you haven't figured quite out yet and what the best design is of your application, right? And so because these scripting languages allow you to be so productive, you can kind of try out different designs and settle on the one that you like the most. And so in practice, if you have an application that consists of that makes use of a lot of list and hash structures, you're going to be vastly more efficient in something like Python compared to C and C++, simply because it's so easy to operate with lists and hashes in Python. And generally, so my experience is that it's often a good idea to start with the scripting languages and then figure out what are the slow parts of your program and convert them to C and C++. So what are the cases where you should stick to a compiled language like C and C++? So the first one is if you have really, really complicated algorithms and data structures that you handle, that you have to take care of. Thanks to the strict typing, you can define these complicated structures, and you can make sure that the entire program is consistent with these data structures. And then, of course, if execution speed is critical, that we've seen from our performance numbers, these compiled languages, they can essentially not be beaten by interpreted languages. Another case is if you really know already how your application design should look like. So if it's slow changing and you expect essentially to do the work only once, then you can also just stick to a compiled language. And in some cases, it can be beneficial to have some properties of compiled languages, like type safety. Right? So if you're in a large development team, it can be beneficial to make sure that the developers have to specify exactly which types they're working with. So some of my personal use cases when I use scripting languages. So if I want to automate tasks, I'm on a Windows computer, for instance, I really like just installing Python and automate some directory restructuring or reading in data or whatever. So essentially getting the power of the Unix environment, and the same thing is true for Bash, getting the power of Unix environment into non-Unix environments. And so your Windows 10 systems, they now have actually Linux included, or at least you can install it on top of it. So there's really now, all of the tools that we're teaching here are actually available more or less natively on your Windows machines as well, making that step a lot less intrusive in a way. And then, of course, if we want to automate boring things with our computer, right, then scripting is perfect. But it's not just that, it's actually also reproducibility. So in my research, it's really important that if I develop a data pipeline and I write a paper about it, and then 1 year later someone asks me, well, how have you actually processed that data again? Right? So the paper isn't quite clear on that specific step. Right? After 1 year, I've forgotten how I've done it. Right? So what I can do is I go back to my script and I check how it's done. And I can reproduce exactly the same results of that complicated data processing. And I can send it to the person who asked and say, well, do it yourself or look it up yourself. Yeah. So, and of course, it's a lot more fun. So if you have the choice between doing a boring task, a boring repetitive task, and coding up a solution that does the task for you, right? Even though they might take the same amount of time, it's a lot more fun to do the programming than the boring task. Okay, but it's not just that, but it's actually also, so this has also been recognized in the industry. And essentially in most industry sectors nowadays that do something IT related, you will find scripting languages used a lot. Did I not show this? Oh, there was a slide on, okay, so I had a slide where I showed the top 5 programming languages. It comes out in the yearly report. And I think it's essentially C, C++, Java, and then it's Python. Right? So this is not just something that is used in the classroom, but it's really, it can be found everywhere now. So some friends of mine work in the financial sectors, and they actually use Python a lot to build up their models. And then once they've been tested and so on, then they implement it, then they have kind of a team that implements it in Java. But a lot of the research and development is being done in Python because it's so dynamic. If you look in mobile apps and web companies, they use Python specifically, but they also use Bash a lot. Just as a main development language. And of course, if you look at engineering, if you're setting up simulation models and research and development, Python is used a lot. So what I want to say is that the skills that you get here is not just useful for universities, but also later on if you go out to the real world. Okay, so one problem that you might get is, what happens if you have kind of mission-critical software? Should you use a scripting language? So imagine your task is to send a rocket to Mars, and your choice is now: shall I use Python to steer the rocket, or shall I use C? Right? What should you choose? And essentially, it boils down to: can you really trust Python and the outputs of Python, right? What is the quality of the Python product to make for these critical operations? Right? And so one argument that you hear is that, well, it's free. You can just download it, so surely the quality must be lower. And there's no one is really responsible for it because it's just can be downloaded free. So who am I going to charge if something goes wrong? So the way these languages are developed is that it's a worldwide effort. So it's an open source project, and everyone can download the source code of Python, and everyone can contribute to the source code of Python. And it's not a single entity, it's not a single company that is responsible if something goes wrong, and if there's a bug in your Python program, in the your Mars rocket crashes. But it's really the entire community that makes sure that the quality is high enough. So essentially the way it works is there's a single repository of the source code of Python and of Bash. And this source code is read and tested and controlled by a huge number of people. And they use exactly the same type of development strategies that I want to advocate at this course. Right? So they will use, many of them use GitHub, many of them use Wikit, and many of them will use the peer review process that you will use later on. And so this design has, this setup of open source project has proven to provide, I would say very, very good quality. And often, so the quality of these packages exceed even the ones of commercial alternatives that you might have. Okay, but I would probably still not write a program in Python to send up a rocket to Mars. It's too risky. Yeah. Any questions on scripting languages compared to compiled languages? No? Is this all known? Is it interesting? Okay. The last thing I want to show today is something called version control system. Has anyone used Git already? Okay, some, yeah. So we will use Git all the time in this course, and I hope, so we will start quite basic, but I think everyone will get more used to it and learn something in this course. Okay, shall I read this out? I think this is quite, it's telling quite a lot actually. So this is Git. It tracks collaborative work on projects through a beautiful distributed graph theory tree model. And then the girl says, cool, how do we use it? And then this person says, no idea. Just memorize these shell commands and type them to sync up. If you get errors, save your work elsewhere, delete the project, and download a fresh copy. Right? So, okay, so the important message is here so Git is a collaborative, a system for working in a collaborative environment. Right? And so typically, this is done for source code. So the idea is that you have one source code repository and many people can contribute to it. The second takeaway message is it's quite complicated to use, and it might be a bit overwhelming at first. But the point is that you can actually just memorize some key commands first and just start using it. And as you get along, you can get more familiar with the system and really make use of the full power of Git. Okay, so how do version control systems work? Essentially, the main idea is that you have your source code on a remote server. In our case, this will be GitHub. And your source code will be it will be essentially called a working copy of that source code. And then, if you want to do some changes to that source code, what you do is you download or update the latest version on your computer that you're working on. You implement these changes, and then you upload these changes, which is called a commit, back to that server. And now this process can be repeated simultaneously by multiple people. Right? So this is how you work as a team. Now, of course, it could be that this person downloads the copy, makes some changes, and at the same time, this person downloads this copy, makes also some changes, but they're actually conflicting changes. Right? But that's fine as long as they haven't uploaded it yet. So what will happen now is, let's say computer 1 uploads his changes. There's no conflicts yet because the conflicting changes are only on computer 2 at the moment. But once computer 2 tries to upload his changes to the server, this is when Git will complain and say, well, there's some conflicting changes here, and you will have to, well, first you will try to merge these conflicts automatically, but if that fails, then it asks the user to resolve these conflicts manually. So when you upload something to GitHub, you might be faced saying, I can't upload it, there's merging conflicts, please fix them manually, and then try again. Okay, so a valid question is now, why don't we just use Dropbox for this? Let's say we have one project, and we all want to collaborate together on one open source project, on one project together. Why don't we just make a Dropbox account and upload our things there? Any ideas? Yeah?
There's going to be a lot of versions uploaded at one point.
Yeah, okay.
It would be very confusing.
So there's a lot of versions. So that's a good point. So one reason is that often when we develop our code, right, we typically break stuff in between, right? So you have an idea for a new feature, then you download the code and you make some changes, but kind of do the development changes until you're done with your feature. In between, your application is essentially going to be broken all the time, right? Up to the point where you've tested everything at the end and you're happy that this is actually now a completed feature. Now, if you worked on a Dropbox folder with 300 or 200 people, right, and everyone would implement their feature, we would essentially constantly end up with a broken setup, and it would be impossible to work. Yeah. So, and there would be many, many different versions flying around, and most of them would just be broken. So that's a key advantage here, right? So what you do is you download your copy, you make your changes until you're really happy with them and happy that other people can see them and everything works, and only then do you upload that stuff back to the main server. So the idea is whatever is here on the main server should always be a working copy that everyone else can use. Yeah, good point. Okay, so what can you use Git for? Essentially, it can be used to organize your work better. You can get old versions of your files again. You can look at the history of that program. And it can be used for collaboration, which I mentioned before, so it works really well for large teams. And of course, and that's quite important as well, it provides kind of a backup, right? So the Git repository, all your source code will be not only on your local computer, but also on the GitHub server or your main repository server, but also copies on the other computers, right? If some of them goes down, you can just download a new copy from GitHub or ask someone else who's developing on that repository. And so what I meant to mention here is this is not just useful for source code and for programming tasks, but it's also useful, for instance, when you write your master or bachelor thesis, right? There's no reason why you shouldn't create a GitHub repository of your directory where you have your master thesis and upload it to GitHub, for instance, to always have a backup of your latest version. And then, maybe in 10 years you want to go back and look to the history of how you wrote your master thesis. Okay, so in this course we will use one specific version control system, and it's called Git. And the reason for that is because it's essentially the main version control system that is now used for open source development. And there's a very good ecosystem out there. So you can that there's online services like GitHub and Bitbucket where you can upload your code, but also there's a lot of installation, support, and help online. And so when you need to install it on your computer, just Google it or use this link here. So let's get started. Let's say we have a directory that we want to now keep track of or use version control system on. So what we do is, let's say my directory of interest is called source. So the first thing I need to do is I need to initialize the version control system for that directory. The way I do it is I type in git init dot. Dot meaning this is just a placeholder for the current directory. So now my my working directory becomes a Git repository. The next thing is that I need to add specific files that should be tracked in that directory. So by default, an empty directory doesn't track any files. So if you make any changes, these changes will just be lost. You need to tell Git specifically which files you want to keep track of. And the way you do that is you type in git add, and then let's say I'm interested in tracking myfile.py and all the text files in this directory. So after that, Git keeps track of any changes of these files. And then, now we make some new changes. Or actually, maybe we should create a first version of these files, that we have a first copy of the current status of the files. And the way you do that is you create a commit. A commit is simply a new snapshot of the current status of your files. So the way you do that is you type in git commit -a simply means everything, all the files that I'm tracking in that folder, and -m means add a message. So every commit, every version that you're creating, you can add a message that explains what you've changed, right? And so in my case, because I haven't changed anything yet, I just want to create a first copy. This is my first commit. And then you can repeat this process. Then you can make some changes and repeat this process. Right? So you can use git status to always get an overview which files have been changed. So let's say we edit our script here, then we type in git status, and it will tell us, okay, myfile.change has some changes that haven't been committed yet. We can look at these changes by typing in git diff. And then once we're happy with them, I can create a new version with the same command as before. So git commit -a -m, and then add some text that explains what has been changed. You can, so over time, right, you will have many, many versions, and you can get an overview of what has changed. You can get essentially a log of all the versions in your folder. So this is one of my projects, and this is actually the lecture courses, the lecture slides, the Git repository of the lecture slides. So you can see every line here represents one version, and you can see what I've changed from one version to the next. And you can also see that each version here has this unique hash key. And you can use these hash key as a reference to go back to that version. So essentially, if you copy and paste this, and then type in git checkout, and then you paste in this hash key here, and then the file that you're interested in, then you get the old version of that file back. And so you can go back to older versions. So far, everything has just been on your local computer. But the important part was to also upload your files to, for instance, to the github.com website. And these are called remote repositories, right? It's your local repository. That's the one that we just created. And there's going to be a remote copy, a remote repository, where we upload all the changes. And so the way you do that is you go to GitHub. Once you've logged in onto GitHub, you can, and you create a new repository, you can clone, or you can, well, in this case here, I'm downloading an existing repository to my local computer. Right? So I just copy this command here somewhere in my shell, and that downloads that repository to my local computer. And I can look at the git log, and I can make changes and upload them again. Right? So this is exactly what I've done before. So you edit the files, and you create a new commit, and then use the command git push origin master to upload your new version on your local system to GitHub, to the remote repository. And then if someone else has made some changes and uploaded them to the remote repository, you want to have your own your local repository updated. Right? The way you do that is you call git pull. So that pulls all the changes from the remote server to your local machine. And so that can be a moment where merge conflicts arise, right? So if someone has pushed changes that are conflicting with your local changes, then this command will fail, and there will be an error message saying you need to resolve some merge conflicts. But this is something that you will learn now in the group assignments, exactly to use these commands and how to resolve merge conflicts, and the mandatory assignments. Okay, and this is just an overview of a few more. And this is essentially a summary of the most important commands that you will learn maybe over the next weeks. Maybe one last thing that I can recommend. There's quite a nice online tutorial. If you go to try.github.io, yeah, it's a short tutorial, I think 10 minutes long, where you essentially practice these commands. Okay, 1 minute left. Are there any questions? No. So just to summarize again, please sign up to this web form. And as far as I know, you know there's this github.uio.no. And I think you might have a username there, but I actually don't think you can use it. So what I think you need to do is you need to go to github.com, create a user there, or if you're already a user, then you can use the existing username, and use the github.com username in the web form. Don't use the github.uio.no username. Otherwise, have fun, and see you next week.